All right, so let's get started. We're going to do a quick pre-recorded lecture on our final topic on influence lines, which is discussing some AASHTO provisions, and then we'll go through some minor additional concepts at the end, looking at indeterminate structures and looking at the resulting influence lines. All the same concepts apply, but I think you'll find there's some interesting applications. We're in lecture today. During the live lecture, we're going to do our exam review. And then on Friday, in case anybody has any additional questions or any problems we'd like to work through, we'll do that as well. But attendance on Friday is going to be optional. Your homework is due today, and that's going to be the last homework before the exam. The topic that we're talking about today strictly isn't on the exam, but there are some good observations that you can make, and so I think this is a pretty worthwhile topic to go through. So let's just recall the Mueller-Breslau principle, because we're going to be using that. You know, the idea that the deflected shape represents to the structure, or to some scale, the influence line. You know, you remove the response, remove from the structure the ability to resist the response that you're looking at, and then you move the structure through a unit deformation, and that resulting shape is the influence line. That'll come into play at the very end when I show you some influence lines for indeterminate structures. But the idea is that the deflected shape represents the influence line. Just make sure that you're good on influence lines for reactions and that you understand, you know, what they look like. I'm actually not going to use that very much today. We're going to be looking at internal shears and moments, but the same process will apply. This is really what we're going to be looking at today with our in-class example with AASHTO. I've actually already drawn the influence line for the example that we're going to do here in a little bit, but just to make sure that everybody's clear on this. So for moment influence lines, you insert a hinge and move that structure such that the hinge experiences a total rotation of 1. So the slope on either side of those linear segments needs to be 1. And for shear, you institute a shear release, and so there's a jump at your point of interest. The total height of that jump is 1, and you have to make that jump such that the slope on each side is equal. And so there's your influence line. Okay, let's talk about bridges. Let's talk about AASHTO. So, you know, if we're talking about highway bridges, which is, again, that was the you know, one of the first reasons that we started looking at influence lines. You know, of course, we need to account for the weight of the vehicular traffic on the bridge. But when you're designing a bridge and you look at the data from weigh and motion studies and what have you, the cars don't really produce any appreciable load demand. It's the trucks that produce the meaningful effects. And specifically, what I'm talking about are what we call in the business exclusion vehicles. So things like concrete mixers, short haul vehicles, any of the vehicles that produce really heavy force effects on structures. Now, do you need to account for every potential type of exclusion vehicle that a bridge would see? No. And that's where AASHTO comes into play. So you've probably heard of AASHTO in your transportation class. If you haven't had transportation, you'll probably have that next semester. AASHTO is the governing body that covers the design of roads and highways and transportation infrastructure in the United States. And so one of the most popular publications from AASHTO is the AASHTO LRFD Bridge Design Specifications. It's the document by which we design highway bridges in the United States. It's the minimum standard that all of the DOTs have to abide by. Every DOT has some unique code provisions and specific requirements in their jurisdiction, but AASHTO is the minimum standard that everybody adheres to. And AASHTO has a live load model that they've developed that simulates the effects of extreme loading on bridges that we see here in the United States. And we call that model the HL93. And the 93 stands really for 1993 when the model was calibrated. Here's what the model looks like. So the model consists of 3 components. So I'm actually going to go in opposite order. So I'm going to start with start at the bottom and work my way up. So first off, there's a design lane. You can sort of think of the design lane as like a stream of traffic. And so we equate that to 640 pounds per foot. And so that's just like a distributed load that we did in the previous example. You just place that distributed load wherever it would generate worst case response. And then you could determine the effects of that response by just taking the distributed load and multiplying it by the associated area under the influence line. And so I think that's pretty easy. For the live load model for the concentrated loads, there's actually two different concentrated load models that we use, and this is something that might be a little different. Instead of a single concentrated load, we have a series of them. Okay, and so I'll start off by talking about the truck. So the truck is what you see here in this this image here. The truck consists of a front axle that weighs 8 kips and a rear axle and a center axle. So the center axle and the rear axle, I'm just calling those the rear axles. Each of those axles weigh 32 kips. So if you wanted to look at this from like a structural analysis, like load model perspective, the load model would look something like this. So you have, an 8 kip concentrated load, and then you have two more concentrated loads. One's 32 kips and the other's 32 kips. 32 kips and 32 kips. And then the distance, so this distance is always kept at 14 feet, but this distance actually varies. It goes from 14 feet to 30 feet. And so the point is, you as the engineer are responsible for varying that distance, but that's actually not very difficult to do in most problems. In most cases, the 14 feet is what you're going to use. In most applications, that's always going to govern, and that's actually going to become clear as we look at our example here in a bit. This truck sometimes has another name. Sometimes it's called the HS2044. The reason why it's called the HS2044 is because the 44 stands for 1944 when the truck was first developed, and the 20 stands for the weight of the two front wheels. So like if the axle is 8 kips, then each wheel weighs 4 kips. And so if an axle weighs 32 kips, then if an axle weighs 32 kips, each wheel weighs 16 kips. So you can think of the front two axles weighing 40 kips, well the front two wheels weigh 20 kips. And so that's where the 2044 comes from. In previous editions of the spec, it used to be that you would just use this truck as the load model. Well, as vehicular loads on highway bridges increased over the years, the idea was to combine this with not only the lane load but also this tandem. And this tandem is meant to simulate heavy concentrated effects on structures. And so the tandem is basically just two 25 kip loads spaced at 4 feet apart. So they're very narrowly spaced a set of loads. So this is the vehicular load model. Back in the day, we used to refer to these by wheel loads, so I would say 4, 16, and 16. But the way that we've updated some of the code provisions that we use in the current version of the spec, we go by axles, so that's why you see 8, 32, and 32. And I want to show you how you would employ these if you were an analyst trying to determine the effects on a real world structure. Okay, so I have an example here I want to go through. Let me go to the example. So I have a beam, and we're going to say this is a simply supported beam, and this is 80 foot long. So imagine that this is an 80-foot long highway bridge, and I can tell you, as somebody who works a lot in this field, and somebody who's trying to educate a group of engineers that if you're interested in bridge engineering, then handling a simply supported bridge is arguably one of the most important skills that you need to be able to assess. So you notice on this problem, like we're doing a real world application with AASHTO provisions, but I don't have a beam that has like hinges and fixed ends and all these crazy boundary conditions. I'm keeping the bridge sort of simple and practical, and I want to go through the real world aspects of how you would do this. Now I'll go ahead and tell you that most software programs, everything that I'm doing will do this automatically, but I want you to kind of understand when a software program spits out this output, I want you to understand that output and understand what values it's producing, what those values represent, why some values are 0, some values are not, and so that'll be kind of my focus here. We have a simply supported beam that's 80 foot long, and I picked a random point on the beam. So we picked this point right here, this point that's 30 foot from the the left support. And what I want to do is I want to take the AASHTO load model that I had on the previous slide, so the truck, the lane, and the tandem, and for each of those three load models, I want to determine my envelopes of shear and my envelopes for moment for each of those. So there's going to be a lot of results for this problem. This isn't a problem where the answer is 2. The answer is a bunch of different values. And so I wanted to focus on using the influence line so much and not really drawing them. I mean, I think by now we should be able to construct this influence line, so I went ahead and just gave it to you. So here you can see the shear influence line. Here you can see the moment influence line. And so we'll go ahead and just use these directly. So let me get out of the slideshow. Let's go to let's go here. Let's make this a little bit bigger. Okay, so here's the problem, and we're going to go through and do our analysis. Now we have 3 components that we need to analyze. We have the truck, we have the lane, and we have the tandem. And so the first thing I'm going to do, I'm actually going to do the lane first, because that's, I think, the easiest one to understand. And so in order to do the lane, all we need are the areas under these influence lines. So, you know, we notice, for instance, that this area is positive, this area is negative. We notice that this area is positive. And so let's go ahead and compute each of these areas. So we'll start off here. I've included some pictures here because I might use them later, so I'll just get these out of the way. So let's do AASHTO lane loading. And remember, we take the lane to be 0.64 kips per foot. Okay, so first off, we need some areas. So let's look at shear first. Shear, S-H-E-A-R. Okay, so for shear, we need the positive area and we need the negative area. So I'll say that the area positive is going to be 1/2. So we're talking about, you know, that triangular region right there. So 1/2 of the base of 50 feet times the height, which is 5/8 or 0.625. And so when you chug that out, you get an area of 15.625. Okay, and then the negative area is 1/2, and then the base is 30 feet, and then the height is negative 0.375. So we get, and maybe I should put the units there that that's feet. And so this is negative 5.625. Okay, and so if I wanted to determine the range for shears, remember from our last example, if you've got dead loads, you would multiply the distributed load times all the areas, and if they're live loads, which that's what these are, you know, all these load models are live loads, then I would just take the live loads and multiply them by the positive area to get the maximum positive response, the negative area to get the negative response. So therefore, our V lane positive is going to be 0.64 kips per foot times 15.625 feet. And so when you chug that out, it actually, this is sort of happenstance. It comes out to a nice pretty number of 10 kips. The next one, the V lane negative, is 0.64 kips per foot times negative 5.62, I forgot the units there, 25 feet. And that comes out to be negative 3.6 kips. Okay, and so one of our answers would then be, you know, V lane positive is 10 kips, V lane negative is negative 3.6 kips. So that point on the structure, that's the range under that lane load. And these values in these load models, again, they just come from basically studying, you know, bridge behavior, collecting data, we call it weigh in motion data, and trying to develop a load model that represents the worst case scenario. So if you're wondering why are these, where does it 0.64 kips per foot comes from? That just comes from studying the real world behavior of bridges and coming up with a load model that's simple but represents, you know, realistic worst case scenarios that we need to deal with. Now for moment, is a little different. So let me underline that. Go back and use a different color. Moment's a little different. And we're going to find this with this particular example, this is going to show up quite a bit. So let's look at moment. Now, for the moment influence line, we notice when you look at it, the entire thing, so we're looking at this line right here, when you look at the influence line, all of the area is positive, okay? And so the area is 1/2, the base is 80 foot, and then the height is 18.75. It's actually 18.75 feet if you want to throw some units on there. So the units don't really matter if you're consistent, but just to be consistent there. Okay, and so that area comes out to be 750. And the units there are feet squared, because what ends up happening is you take the kips per foot and multiply it times that, and it comes out in units a moment. It comes out in foot kips. All right, but the point I want to make here is about the area. So when we looked at shear, we had a positive area and we had a negative area. But with moment, we have a positive area, but we have no negative area. There is no negative area. So maybe what I'll do is rewrite it like this. I'll say area positive equals this, and the negative area is 0. There is no negative area. So what that means is the lane load has a positive moment of 0.64 kips per foot times this area of 750. And when you chug that out, you'll get a lane load moment of 480 foot kips, but the lane load negative moment is 0. Now, what that means from a behavioral perspective is, this is a simply supported beam. Remember, let's go back to the basics of an influence line. I'm taking a single unit load and I'm moving it across the structure. Think about how this structure would deform, how it would bend if you move that load. It's always going to smile. It's always going to produce a smiley face, a bended shape or deflected shape, something like that. There is nowhere that I can place a load on the beam that would cause it to frown. So none of the loads that I place will cause negative moment. I'm always going to have a range, and this is going to be true for the truck and the tandem as well, that my lane load positive moment is going to be some value, so 480 foot kips, but the negative moments are always going to be 0, okay? And the reason why is because of the way this beam is structured. This is a simply supported beam, and the simply supported beam is always going to produce positive bending. That isn't always the case. If you have an indeterminate structure or you have multi-span arrangements or something like that, it's very possible to have negative moments as well. In fact, on continuous span indeterminate structures, you will have positive and negative moments. That is a fact. But for this particular problem, that's not going to be the case. That's why I'm always going to have the negative moment is always going to be 0. So, and your software output that I'll show you here in a bit, it kind of does the same thing. So, just something to think about. Okay, so that's your range for your lane load. So I've got a positive and negative shear, a positive and negative moment. Now we need to look at the truck and the tandem. Okay, and what I'm going to do is I'm actually going to do the tandem first. I think the tandem's a little easier. All right, so let me move this here. Let's move this here. So this is where the little images come into play. So what I'm doing here is I'm using these images as sort of just a visual of how this would work. So here's the bridge, right? And here's the influence line for shear. Okay, so I have this here on the screen. Let's move that there. Okay, and think of this tandem. This tandem is literally driving across the bridge. Okay, now I've got two 25 kip axles, 2 point loads spaced 4 feet apart. Okay, so let's think about our sign conventions, right? Okay, so this is positive shear, this is negative shear. Okay, so let's take each of these one at a time. Let's start off with positive shear. Okay, where would I place this load to generate the worst case positive shear? Well, what I'm thinking is, look at the influence line. I'd probably place it like somewhere like right there. I'd place one load directly over that point right there, and then the other one would go like right there, 4 feet apart. So basically what I've got to deal with is I've got some linear interpolation I have to figure out on my influence line. So let me get this truck out of the way here. So I know this value from the influence line is 0.625. That's easy. Let me maybe if I could write here 625. That's easy. What about this one? Okay, how do I figure that out? Well, this just involves some linear interpolation. So let's look at some things. Okay, this dimension here from the other part of the problem. This is 50 feet. If you and let me draw this out. This dimension here is 50 feet. Okay, and I'm just getting that from right here, from that's the left side of the beam. Okay, so that's 50 feet. All right, so if this is 50 feet, then what is this dimension here? Okay, well, let's see. Let me take my tandem here and blow it up a little bit. Okay, the tandem axles are spaced 4 feet apart. So I know that this dimension here is 4 feet. So this is 46 feet. Okay, so how do I find this unknown value here? Well, what I'm going to do is I'm going to take 0.625 and multiply it by 46 over 50. It's that simple. So 0.625 times 46 over 50 is 0.575. And that's all there is to it. So this value here is 0.575. And that's it. That's all there is to it. So make that a little smaller here. Move that out of the way. And we'll take this and sort of move it up here a little bit. So if I want my, say, V tandem, if I want the positive result, remember each of the axles weighs 25 kips. I'm taking 25 kips times my values on the influence line. So 0.625 plus 25 kips times 0.575. And that's all there is to it. That is how I would determine my positive tandem. And again, that's a live load, so it's concentrated load, so it's concentrated loads times the values on the influence line, not times the areas. And so when I chug that out, I'm going to get, let's see, what do I get? Actually comes out to a nice round number of 30 kips. Again, that's just a happenstance with this problem. So for V tandem negative, so what am I going to do here? Well, I'm going to take each of those loads times the negative values, because here, if you look here at my image, if I want to produce the worst case positive shear, I'd probably put the tandem there. If I want to produce the worst case negative shear, I'd probably put it there, because that's where the highest negative values on the influence line show up. So I know that this one is 0.375. I then need to know what's this. And that's 4 feet, so I need to know what's that. And the way that you do that is the same way that you did it up here. I'm going to take 0.375, and instead of taking it times 46 over 50, I'm going to take 0.375, multiplying it by 26 over 30. Because this dimension here is 26 feet. And that's all there is to it. That's how the linear interpolation works. And so in some future examples, I might breeze through the linear interpolation a little bit and just sort of show you the logic. I just wanted to kind of walk through how some of those values are derived. So when you do the linear interpolation here, you get a value of 0.325. So this is 0.325. So your tandem, your negative tandem is going to be 25 kips times 0.375 plus 25 kips times 0.325. And so when you chug that out, you'll get minus 17.5 kips. And there you go. There's your tandem envelope. For the truck, you're going to kind of do the same thing. One of the things I'll point out about the truck that I kind of glossed over with the tandem. So if you look at the tandem is two 25 kip axles spaced at 4 feet apart. So it's symmetric. Like it doesn't really matter which way it faces. Well, the truck, see here's the thing about the truck. This is the image I showed you, and I had the front axle over here on the left. There's nothing to say that the truck can't face the other way. You know, I guess my flipping here isn't working on the image. In other words, like maybe I'll draw it down here. So I have the truck drawn like this. So 32 kips, 32 kips. Okay? There is no reason whatsoever why the truck can't look like this. In other words, here's the one image. That's the best truck you're going to get out of me. Well, why can't the truck face the other way, right? Why can't the truck, maybe I'll try this. Maybe I'll try it like this. The truck could do that. The truck could face the other way. And so there's nothing to say that when you're positioning this truck that it has to face a certain direction. You put it whichever way you need in order to generate the worst case response. So if I'm looking here at the influence line, okay, so let's take positive shear. Okay, let me move this over a little bit. Okay, what I'm thinking is if I want to generate positive shear, what I kind of need to do is I kind of need to put that 32 kip axle there. I need to put the heaviest axle on the heaviest point that I can find. And as for future points, okay, let's look here. So what about my next axle? This axle probably needs to be 32 kips, and this axle needs to be 8 kips. And so, I'm thinking put the heaviest loads on the highest values that I can. Okay, now let's talk about distances. Okay, this distance is constant. That's 14 feet. Okay, that's that distance right there. Okay, now let's look at this part right here. This says that we have to vary the axle spacing anywhere from 14 feet to 30 feet. Okay, so the question is, if I look at this problem, what do I make this distance? Do I make it 14 feet, or do I make it 30 feet, or do I make it somewhere in between? Well, let's just take the two extremes. Let's take 30 feet. If I made that distance 30 feet, I would be pushing those two loads further to the right. Which, what would that do? That would reduce the shear. Okay, I'm trying to generate worst case responses. So it seems to make sense to bunch those loads together as close as possible. Don't spread them apart, because that's going to generate the worst case response. So I can go ahead and tell you that the worst case response is going to be if this is 14 feet, not if it's 30 feet. Okay, or if it's anything in between. I want those loads to be as close together as possible. And so once I've determined the location, I've got that figured out. All I've got to then do is say, okay, what are my values on my influence line when this is 14 feet and 14 feet? And then just do the same thing I just did. Okay? And so I can go ahead and tell you, so we know this one right there, we know that's 0.625. I've already done the interpolation for the others. Did it the same way I did it before. So this is 0.45. And this is 0.275. Okay? And so if you want to determine maximum truck shear, so V truck positive, what are you going to get? Okay, you're going to get 32 kips times 0.625 plus 32 kips times 0.45 plus 8 kips times 0.275. And so when you chug that out, 32 times that plus 32 times that, etc., you get a value of 43.2 kips. And that's the maximum shear that you could generate with that truck. So if that truck's moving across the bridge, that's the maximum shear, maximum positive shear you could get at our point of interest. For negative shear, truck, negative, we just kind of do the same thing. So we're going to have this is 14 feet, and this is 14 feet. 14 feet. And we need to figure out those values and the same thing. So once you've figured out the process, the rest just kind of becomes sort of grunt work. So this is, 0.375. This one is 0.2, and these are all negative. This is a tiny one. This is 0.025. Okay? And so you think to yourself, where am I going to place the truck? Like what direction and on what axles? Put the heaviest axles on the heaviest or on the largest values on the influence line. So the 32 kips is going to go there. That one's going to be 32 kips, and that one's going to be 8 kips. That's where I'm going to place the truck on the beam to generate that worst case shear. And so 32 kips times negative 0.375 plus 32 kips times negative 0.2 plus 8 kips times negative 0.025. And so when you chug that out, you'll get negative 19.2 kips. And so there you go. Now we have an envelope here. We've got our positive and negative shears from the tandem, positive, negative shears from the truck, and before we had positive and negative shears from the lane. So that's all of our envelopes for shear. Now we just got to do the moment. And so maybe what I'll do is I'll sort of formalize this a little bit. So V tandem positive is 30 kips. Okay, there we go. All right, so the only thing left to do is to do this and to figure this out for the moment. Okay, now before we go through and chug all this out, we have to recognize one thing. So when we looked at the shear, we had positive and negative values. Okay, we had a positive 30 kips and negative 17.5 kips, and same thing with the truck and the tandem and the lane and all that. But with the moment, we had a positive value, but for negative it was always 0. Remember, for the lane, there was no place that we could put a load and generate a negative response. So before we even start doing any math, we should probably recognize that M truck negative is going to be M tandem negative is going to be 0. And that's going to be an answer right there. There's nowhere that we can place a load and generate negative moment. Just nowhere. That's not going to happen. Okay? Now, what makes moment maybe a tad trickier is when you're looking at your positive moment, there is a possibility of other cases. Okay? Let's take the tandem one, because I think the tandem one is the easier one to sort of investigate. Okay? So first off, I could go ahead and tell you that I'm going to place, so remember, what's our tandem look like? We have a 25 kip axle, a 25 kip axle, and those distances are, those axles are 4 feet apart. Okay, so if I'm trying to generate worst case moment, I can go ahead and tell you I'm gonna put one of those axle loads like right on that high index. So there'd be no reason not to. That's the highest index on the influence line. The question is, what about the others, or what about the other axle? In other words, do I place that here, or do I place it here? Now, I've done a pretty good job of drawing this influence line to some reasonable scale, and so I think you could kind of view by inspection that this influence line value is higher than this one. But just in case you're unsure, you can always just chug it out, right? This is a tandem, so we know this dimension is 4 feet, and we know this dimension is 4 feet. So I can use the same linear interpolation process I did before, and I can determine the values on the influence line. And so this one, when you chug it out, this one ends up being 17.25, and this one ends up being actually 16.25. So if I'm going to place, and I guess I should put the units on these. These are all feet. Okay. So if I'm placing a tandem load on this beam, I would put the first axle right there, and then I'd put the second axle right there. In other words, I'd put those values over the higher indices that I can generate, and that's going to generate my highest tandem moments. Now, sorry, 25 kips, and so to generate maximum positive moment, I'm going to get 25 kips times 18.75 plus 25 kips times 17.25, and those are feet. And so M tandem positive is, let's see, when you chug that out, you're going to get 900 foot kips. And so that's one of our answers right there. And so we've already figured out that envelope. We know that the positive is 900 and the negative is 0. So that one's already figured out. Now, for the truck, this is what I find is the easiest way to, this is the way that I find is the easiest to handle this, to be systematic, is I know I'm going to place one of my axles right here over this peak. I know I'm going to do that, okay? And so what I find is the easiest to deal with from a systematic perspective is I also know that since I'm going to keep my axle spacing at 14 feet, I'm going to lump those loads close together. What I'll do is I'm just going to determine the values on the influence line at distances 14 feet apart. So I'm just going to take the influence line, I'm going to split it up into 14 feet. And I'm just going to interpolate the values on the resulting values on the influence line, and let's just see what I get. Okay, so once you go through that process, so we know that one's 18.75. What do you get for all the others? Okay, and so I did that previously before the recording, and I got 13.25 here. I got 8.25 here. And then on the other side, I got 10, and I got 1.25. Those are in feet. And so then the question becomes, okay, where do I place the truck? Okay, so look at the, let's go back to what the truck looks like. Okay, so here's the truck. It's 8 kips, 32 kips, and 32 kips. Okay, we know this dimension is 14 feet, and we know that this dimension is 14 feet to 30 feet, but for being effective for this problem, we're going to use the 14. Okay, so what I'm going to do is just one other thing to recognize: I can face the truck whichever way I want, and so really what I need to do is just start placing these axles in order to generate the worst case response. In other words, I'm going to have an axle there. Okay, that's just a fact. I've got to have an axle there. That's the heaviest index on my influence line. And if I'm trying to maximize response, I'm going to make this 32 kips. All right. What about the next one? Okay. Well, what's my next highest index on the influence line? Hold on for one sec. I'm getting a call on my other line. My apologies. Okay. So, I've got my 32 kips on my highest index. What's my next highest index? It's the 13.25. I'm going to put a 32 kips there. Okay. Then I look at my remaining indices. What's my next highest index? It's not over here. It's not the 8.25. It's the 10. So I'll put my 8 kips there. So you just rank it in order and place your loads there. Now again, you got to make sure that you're placing the loads in such a fashion that the truck's actually well defined. Like this has to be, 14 feet, and this has to be 14 feet. As long as you're doing that, you're good. All right. So in order to compute this, we're just going to, go along here. I've got 8 kips times an index of 10 plus 32 kips times an index of 18.75 plus 32 kips times an index of 13.25. And that's how you figure this out. And that's how software programs do this, is they'll just sort of iterate through all of those options and just, pick the one that's going to generate the worst case response. And so M truck, once you chug everything out, you're going to get an answer of, 1104 foot kips. And that's basically all there is to it. So, just to show you some ways that we could organize this, and I've got an image here in a second that I'll kind of go along with this. If you look at this, I'm going to show you a way that we could organize this, and you'll see where I'm coming from. Let's just take the shears. Okay. So a way that we might organize this for real world use is we might pick a point on the structure. So we picked like 30 feet. Okay. And I'm saying the word 30 feet because if you go up top, it was 30 foot, from the support over here on the left. So we'll say X is 30 feet. And so what I might do is I might say, okay, let's list my, truck shears, and let me move this down because I don't want to confuse things. Okay, so let's list my truck shears, and so I'm going to have a positive value and a negative value, and so we got like 43.2, and we got negative 19.2, right? And then maybe what we'll do is we'll list our, our lane shears, and you can list this in whatever order you want. And so we have a positive and a negative, and so this might be 10 and, negative 3.6. And then we have our tandem, right? And then we'll have a positive and negative, and so our tandem we ended up getting like 30 and minus 17.5. And so this might be how I would list these values if I was doing this as a table. And so this would be, let me clean this up a little bit, make it a little prettier. Okay, so, I need to turn my pen on. And actually, I'm going to do one other thing. You'll see what I'm doing here in a sec. Bear with me. Okay, so what this table might represent, this might be my live load shear envelope, shear. Okay, and so let's just sort of digest what I have here in the table. So I picked a point on the beam. So we said, 30 foot from that support, and 30 foot from that support, I have a positive and negative shear for the truck. I have a positive and negative shear for the lane. I have a positive and negative shear for the tandem. And that's good for that one point. And if I was a bridge designer, I might ask, okay, maybe I need more points. Maybe I need, to do this again for 20 feet, or maybe I need to do it for 10 feet, or at the support, or, 40, or whatever. This beam was 80 foot long, and so I would have an entire table of values. I want to show you something here. This is from a study that I did a while back. Myself and a few other authors, we worked on a study where we did a full-blown bridge design in this report, and this is actually just an example table from a different bridge. The bridge isn't the same span. This bridge, I believe, was 60 foot long. But what we did here is, I'm organizing those values in this fashion. These are the shears that we got from that analysis. And so I believe this bridge was 60 foot long in the study. I did this report a few years ago. But you can see I'm organizing that in this fashion. So this right here, this term X over L, these are the 10th points I was talking about. So I might have, 0 foot, 6 foot, 12 foot, 18 foot, all the way to 60 foot. And for a given row, like let's just pick this row here. Actually, I'm going to use the highlighter tool. And so let's say for this row here, that's a particular row. See how we've got, we've got a positive and negative shear for the truck, a positive negative shear for the lane, a positive negative shear for the tandem. That is my envelopes. What's going on right here? What are those? Those are the dead loads. This particular bridge has 3 dead loads we have to consider. They're called DC1, DC2, and DW. DW is your future wearing surface, and the DC is basically the structure self-weight. You have to apply it in 2 stages. That's bridge engineering land for another day. But the point I want to make is that the dead loads, they just have values. But the live loads, if you're looking at the truck or the lane or the tandem, they have a range of values. Okay, and this is what the table looks like if you're looking at shears. Okay, and this is a simply supported bridge, so it's very similar. If you look at moments, this is what the table looks like. And look, the other thing I wanted to point out is look at this. Let me clean that box up. Look at this. So this is, for the truck. But look at the negative column. They're all zeros because this was a similar instance, right? You can't generate negative moments for a simply supported structure like this, hence why they're all zero. Same thing for the lane and for the tandem. For moments, you also have to do a fatigue truck analysis, but you get sort of the same boat there. So hopefully you kind of get a peek into how this works in real life. I mean, there's a lot more that you have to do in bridge engineering land to make this work. I just kind of wanted to introduce the topic. Let's see, how am I doing on time? Oh, I'm doing perfect. I do want to just mention one final thing right here in regards to influence lines for indeterminate beams. So for indeterminate beams, so remember, if we go back to the Mueller-Breslau principle, it does work for indeterminate beams, but the influence lines are not straight, they're curved. The reason why is because, if let's take the influence line for the reaction at A. If I remove from the structure the ability to resist the reaction at A, the structure's still stable. Like, I can still put loads on that beam. It's not like before where if you had a simply supported beam and you kicked off one of the rollers, that beam's falling apart. This one, that's not the case. And so if I take that beam and I move it through a displacement, I'm actually deforming the beam. I'm actually bending it. So that's why the reaction influence line for A has got this curve to it. Now, it still follows the same rules, right? You still get, what is it? You get, 1 here, and you get 0 here. I know the lines, I drew this in PowerPoint, so I know it's a little off, but that you kind of get the idea. Same thing for the influence line for the reaction at B, right? This is 0, this is 0, this is 1. Same process, but the influence lines look curved because the structure's indeterminate. And this is really the key right here. The only time influence lines are curved is when the structures are indeterminate. And that's a really good big point I want to make on the exam. But even though you can find the same philosophy, and I say the exam, we're not going to have any indeterminate problems on the exam, but I'm just talking about just in general. Let's take shear, for instance. Same conclusion, right? 0, 0, 0 at all the supports. The total jump is 1, but again, it's still curved because it's indeterminate. Moment, 0, 0, 0, and the slope of this line and the slope right there at that support is 1. Or at that internal release is 1, but again, same process. All right, that's all I have. I know that the video probably went a little longer than I'd like, but I kind of wanted to go through some of the details. Again, this isn't going to be on the exam. This is just sort of food for thought for as you prepare for the exam. It's not on the exam, but it's just some more practice that basically the idea is if you get this, you'd certainly be fine on the exam. Okay, that's all I have. I will see you all in class actually here in about an hour. That's all I have. Let me turn this. All right, see you in a bit.